really excited to introduce Howard Wu, who's going to be talking about DIZK. We actually got a chance to sit down with Howard, I think 3 weeks ago or so, and do an episode on, well, we were talking about zkSNARKs, but we did get a chance to touch on this, so I'm definitely excited about this talk. Cool. Take it away.
Thanks. Hi, so I'm Howard, and I'm a researcher at Skipper Lab in Berkeley and also a partner at Decrypt. Today I'm going to be talking about DIZK, and DIZK is a distributed zero-knowledge proof system. This is joint work actually done with Wenting, Alessandro, Raluca, and Jan. To begin with, you're probably asking, and we've also had a lot of great discussions earlier today on what is a zero-knowledge proof. And I will give you my rendition on this. A zero-knowledge proof involves two parties. You have a prover and a verifier. And both the prover and the verifier know some public function f, as well as a claimed output y. And the prover says, hey, I know x such that f of x is equal to y. You can think of x as your private input in this case. And the verifier wants to be convinced of this, and so he or she will then challenge the prover. They play this interactive game with each other, after which time the prover will convince the verifier if indeed they know this secret. Now, there's one particular type of zero-knowledge proof that has recently gained a significant amount of attention, and this is zkSNARKs. A zkSNARK is a zero-knowledge proof with a few additional guarantees. For one, you have non-interactivity. So what this means is that the prover only needs to provide a proof to convince the verifier that they know the private input x. Secondly, you have succinctness. And what this means is that the proof itself is small in size, and the verification time here is fast. Now, one particular type of zkSNARK that we're going to talk about today, and also is very commonly used in deployment today in industry, is that of preprocessing zkSNARKs. And a preprocessing zkSNARK has a function, a setup, that takes as input a public function f, and it produces two outputs. One is a proving key, and the other is a verification key. I try to use size here to show kind of the differences in costs on memory and time, and the proving key here is going to be significantly larger than the verification key. Now, zkSNARKs in general have many interesting applications, two of which we will discuss today. So the first application that we're going to look at is peer-to-peer payments. And suppose you have Alice and Bob. Alice wants to pay Bob, let's say, $1. And she may use a blockchain to facilitate this payment. As you will commonly think, this would actually reveal a lot of information. First off, you learn about the addresses that are involved. And so you learn that Alice is the sender, that Bob is the receiver, and that the payment amount here is for $1. Instead, what you could do is actually encrypt the contents of the payment. And so if you do that, then you could actually get anonymous peer-to-peer payments. But to ensure the validity of the payment, in this case, you would use a zero-knowledge proof, a zkSNARK, that would be attached with the transaction to ensure that those encrypted contents indeed are valid and justify a proper payment. This is a protocol called Zero-Cash, and it's manifested in industry as Zcash. Let's look at a second application. So suppose you want to use a smart contract to run a publicly verifiable computation. We actually just saw in the previous talk with Socrates a very nice demonstration of potential use cases and potential directions for zkSNARKs in terms of Ethereum. And the issue is that today, when you invoke a smart contract, you have to require all the validators to rerun this computation. So a more scalable approach is actually for the caller to run the computation off-chain and instead send along the result along with a proof attesting to the validity of the result. Then the validators would only need to check the proof, which we've established here is cheap. Now, these are only 2 applications of zero-knowledge proofs, and don't be offended if your favorite application wasn't presented here. These 2 applications were actually chosen very specifically to motivate our problem, which I'm now going to address. So we have some good news and some bad news. Well, if we plot the circuit sizes of the applications that we just discussed, we'll see that the private payment application requires about 1 million gates. And this is great. It's actually very practical, and this is why you see things like Zcash in deployment today. Now, if we look at a typical smart contract execution, and we try to map it into the circuit world, we find that the actual cost of these things is around 100 million gates. And for a larger smart contract execution, we find ourselves using billions of gates. So unfortunately, current monolithic zkSNARK implementations run out of memory at around 10 million gates. And this makes this particular application, smart contract executions, just out of reach from current techniques. So we asked ourselves, what could be a stepping stone for enabling applications such as this? And this is where I present here DIZK. DIZK is a zero-knowledge proof system that is, 1, distributed, meaning it enables the execution of a zkSNARK setup and prover across a compute cluster. Second, it is scalable, so it reaches heretofore unreachable circuit sizes, up to billions of gates. And the intuition that we have and the pattern that we see is that as we double the number of machines, we effectively support twice the circuit size. The third point is that this is parallel. So it speeds up the time it takes to generate a proof. And again, the pattern that we see is that as we double the number of machines, the general computation itself is roughly twice as fast. So how did we do it? Well, the approach that we took was to take a monolithic zkSNARK, namely one by Jens Groth from 2016, and distributed it on a cluster of machines. Now, this approach seems quite simple. However, it turns out there were a lot of challenges to distributing the protocol. We chose Groth 16 specifically because it is highly efficient and currently offers the smallest zkSNARK proof size. And in general, we had to tailor our architecture at every level to ensure that our protocol could adequately demonstrate scalability and parallelism. So let's talk about, and let me walk you through some of these challenges that we face now. So in terms of challenges, let's take this zkSNARK diagram, and I want to point out that the verifier in this context is extremely small and really cheap to run. Therefore, we turn our attention to the setup and the prover. At first glance, we'd probably want to spin up a cluster of machines and run the setup and prover on it. And next, we'd probably want to use a distributed data structure to represent our public function f, the proving key, and our secret input. This looks all right, however, it's not. And there's several challenges that arise with this current setup. The first is that we're multiplying polynomials of degree that are in the billions. Second, we're representing these polynomials as terabit-sized arrays. Third, we're accessing large pools of shared memory in complex patterns. And fourth, we're synchronizing shared state that incurs significant network delays. All in all, these fundamental challenges are things that we need to overcome, and we do so in the following way. So we start with the setup. And it turns out it's not enough to keep the subcomponents of the setup itself monolithic. And so we distribute the setup by implementing distributed algorithms for the subcomponents of the setup. The distributed setup then outputs a proving key, a distributed proving key, and a small verification key. Just as before, we distribute the prover by distributing the monolithic subcomponents of the prover. And lastly, we will verify that the proof is valid. And again, we forego distributing this step as it's extremely cheap to run. So for time's sake, I want to focus on one critical part of our system, and that's the distributed prover. You will find details of all of these distributed techniques in the paper for DIZK. It's available online, and I'll show you the link at the end. But today I really want to go over one critical component in this system, and that's namely the witness reduction. So the witness reduction, I will show you some of the off-the-shelf approaches that you can use to compute this reduction. And then I will show you the tailored approach that we use to make this witness reduction both scalable and parallel. So to efficiently compute the zkSNARK proof, we need the circuit we started with in polynomial form. And namely, the equation that we want to evaluate here is this one. If you haven't seen this equation before, this is an important equation introduced in GGPR 13 that defines a quadratic arithmetic program which has to do with arithmetization for circuits. And if we zoom in on this equation, there are 3 terms that need to be efficiently represented and evaluated in order to perform the witness reduction. Also notice that these terms have summations from 0 to n, where n is in the billions. So I'll focus on how we efficiently evaluate these summations. Note that the arithmetic operations outside of these 3 terms will make use of distributed FFTs, which again you can find it in the paper. And zooming in on one of these terms, we see that there are 2 components, a matrix A and a vector Z. The matrix A represents one part of the input wires comprising our circuit, and the vector Z is a satisfying assignment for the circuit. You can think of it kind of like a combination of the public inputs and the private inputs that we discussed earlier. So as a straw man for computing this, we might start by representing our matrix A as follows and representing our vector Z as follows. We'll represent these as matrices and vectors in their canonical form, and to evaluate the summation, we need to join the elements by their index I. So as a strawman approach, we may partition our matrix A row-wise and our vector Z element-wise. Next, we'll join our partitions row-wise, so A0 with Z0, A1 with Z1, ... down to AN with ZN. And this generates a join table that will look like this. It appears quite uniform in cost, with each entry now independent of all of the other entries. But it turns out that this isn't the case. And let's see why. So here's an example of the data that would be stored in this case. And because of the nature of our circuit representation, our matrix is what we call almost sparse. And this means that most rows and columns are sparse. However, there will always be a handful that are dense. So in this case, think of the red entries as like your dense entries and the green ones as your sparse entries. If we partitioned our matrix column-wise to compute, for the cluster to compute, the second column would be slow and straggle, causing all the other machines to wait on it to finish its task. This is obviously a bad thing, and so this is probably not the best way to look at it. If we tried the other approach of partitioning this matrix row-wise, well, again, we'll actually run into the same problem with the first row as our straggler and causing all of the other machines to wait on it to finish its task. We studied all of the off-the-shelf approaches to address this problem currently, and this is mainly trying to address a problem of data skew, and we benchmarked them across varying circuit sizes and also across varying numbers of machines to determine their feasibility. And the approach that we took with these was to basically say, let's replicate and partition the data so that the computation is distributed evenly. This is what all of the off-the-shelf approaches try to do from it's like a systems level approach. So the first one that we looked at was block join. And block join is one of the common techniques to address data skew. What it does is it will replicate each entry in one distributed data set across every machine. So the hope is that when you're joined with the other distributed data set, the partitions will be more or less evenly spread across the machines. And what we end up with is a join table that looks like this. So at first glance, this table looks quite large, and indeed it is. Block join has performed n+1 times the number of partition replications. And recall that n+1 here is, again, in the billions. And so now every partition here is dense, and therefore the computation is uniform. Well, that's true. However, the table is also now huge and impractical to compute. So this does not work for our system. And so we turn to other off-the-shelf approaches. Next, we benchmarked another common technique to address data skew that's called skew join. And skew join takes a more fine-grained approach by first computing usage statistics, and it will replicate frequently used entries for every machine. This sounds more reasonable, and indeed in most cases it really is. However, for our system, it turns out this provides us with minimal advantage, and let's see why. So if our matrix A is partitioned row-wise, and we perform a skew join operation with vector z, we see that each partition only needs to access one unique element from the vector z. And in this case, skew join is actually functionally equivalent to the strawman approach we saw earlier. Now, if our matrix A is partitioned column-wise and we perform a skew join with vector z, we see that each partition now needs access to every unique element from the vector z. In this case, we actually find that skew join then is basically equivalent to block join, and that was an approach that we saw earlier that we had deemed to be one that's dense and therefore impractical for our use cases. So no matter how we organize the data here, off-the-shelf approaches will cause unnecessary replications that blow up our memory cost requirements, and it makes it impossible to scale the system. Actually, in fact, I think this approach that we used at the time, it turns out it wouldn't even scale beyond like 50 million constraints on 128 machines. And so until then, this is really it actually turns out to be twice as slow as our tailored approach, and I'm going to describe that next. So for the tailored approach, we implemented one that basically can evaluate our witness reduction and preserve scalability and parallelism. The approach that we took was to isolate and transform the data so that the computation is distributed evenly. And let me show you a high-level picture of how we do this. So we start with the almost sparse matrix A from before, and we perform now a pre-processing step. This will get us our density counts, and so this will get us density counts for each of the partitions that are in this matrix, and these statistics will inform our system how to isolate the dense vectors from the sparse vectors, which we do next. So using this density count information, our system will then split dense vectors into sparse partitions. Now to perform the join operation between matrix A and vector z, we will perform what we call a hybrid join. A hybrid join will replicate only a handful of the unique elements from vector z. As we said, our matrix A here is almost sparse. And notice now that in our case, each partition actually just has one dense computation to perform. So our replication factor was minimal, and as our approach is able to preserve the almost sparse structural representation of matrix A, we find that this actually ends up being quite well. This enables us to join our data and compute the summations from before without stragglers. And in practice, for the same number of machines, we find that our tailored approach now enables us to reach billions of gates, where off-the-shelf approaches, we had said, kept us away from being in the billions of gates. And so along with other distributed subcomponents that were described in this paper, we're able to architect a zero-knowledge proof system that is actually scalable and parallel. So we implemented DIZK, and we used a cluster compute framework called Apache Spark. Our system is written in Java with approximately 10,000 lines of code. And we ran our experiments on EC2 using R3 8X large instances. These each have 32 virtual CPUs and 244 gigabytes of memory. Our evaluations showed us some really interesting patterns and properties. So in terms of the largest supported circuit size, well, we first evaluated this against libsnark. Libsnark is a C++ library for zkSNARKs, And we profiled this in our environment and found that it would reach approximately 4 million gates. When we profiled DIZK across a different number of machines, we found that we were able to reach approximately 2 billion gates with 256 machines. And the pattern that we saw here is that as we double the number of machines, we were able to support twice the circuit size. So this then led us to ask, could we compute up to these large circuit sizes in a time-efficient manner? It's one thing to just be able to reach that. It's another to be able to reach that in a practical manner. And that's where we look at scalability. So here we have two graphs. On the left is the setup, and on the right is the prover. Note that this is a log-log scale graph, and so if we follow the trend on one of these lines, namely the one for 256 machines, we find that the slope is approximately equal to 1. So this is linear, approximately linear. And the pattern that we see is that as we double the circuit size, we're able to support twice the, or we're able to compute, it takes roughly twice the time to compute. And that's a very nice property to have. Here again, we plot the same data now, but show the number of machines on the x-axis and plot the circuit size. So this is trying to demonstrate parallelism. And again, on the left, we have the setup, and on the right, we have the prover. If we follow this line at 2 to the 26, this green line, the pattern that we see here is that as we double the number of machines, this computation is actually approximately twice as fast. Again, this is a terrific property of the system and something that we find very, that would be very necessary for computing large instances. And so in conclusion, we found that, that prior zkSNARK support maximum circuit sizes in the millions of gates at an amortized cost per gate of 1 millisecond. And we find with our techniques that DIZK is able to support maximum circuit sizes in the billions of gates at an amortized cost per gate of approximately 10 microseconds. The full paper is available on crypto ePrint. And I'm also proud to say that we've released DIZK as an open source library on GitHub. You can find it by going to DIZK.org. And we've put a lot of hard work into making this library available to the public with a convenient profiling infrastructure so that you can replicate these results. But you can also use it to build new and interesting applications with DIZK. And lastly, I'd like to leave you with 2 open questions. So the first question is with regards to even larger circuits. What techniques will get us to trillions of gates, if any? And based on napkin math, if you look at the current techniques that we use, we need approximately 100,000 machines in the best case scenario, which frankly is too many. The second open question is with regards to other succinct zero-knowledge proofs. So how efficiently can other succinct zero-knowledge proofs be distributed? And you can look at Starks or bullet proofs. Our techniques are likely an excellent starting point. They share a lot of common primitives below, and it seems to be an area that would be very fruitful to study further. And so with that, I'd like to conclude, and thanks for your attention.
Hello, cool. So here's some questions.
Hi, thank you for the great talk. What is the input for DIZK? So if I wanted to use that, what would I have to pass into it to compile? Or
Yeah, so to use the system, you basically need to have like a problem, like some function that you're trying to compute, and then you have to map that into a circuit world. Once you have that, you'll have like your public inputs and your private inputs that you need to provide. All of this would then run on either your personal machine or on a cluster machine where you could, it can really be operated on any system that supports the Java, like JVM in this case. And in general, like as long as you have all the dependencies that the library requires you to do, then that's kind of all the pieces that you need.
So it's this R1 CS constraint system, basically, that's the input to the DIZK?
Yeah, so the current library supports like rank 1 constraint systems, and we use that and map it to like quadratic or reduce it to quadratic arithmetic programs. If you'd like to try other approaches, you're also welcome to contribute on that front, but right now that's the MP language that we support. Yeah.
Thank you for the great talk. Looking at the performance graphs, after after a certain amount of executors, it looks like the system reaches some kind of diminishing returns. So after, I see that for smaller instances, and after 128, and you go to 256 in the, yeah, in this.
Oops. 1 second.
Yeah.
Animations are slow. They should have like a scroll feature. Okay.
In the next graph, I believe. Yeah, here. I noticed that the setup and the provers in the lower part of the graphs, they start taking longer.
Yeah.
Is there a reason to that? Is it that similar to other parallel, how after a while adding more CPUs does not make the parallelism better and it's just computational overhead?
Yeah, absolutely. That's a really good question. I'm going to move it to this previous graph and just kind of show you on the red curve here. It's the same property that you're pointing out there. The trade-off that's being made is that as you grow the number of machines, you basically start to have this setup cost overhead. And not to be confused with the distributed setup, it's like the actual cost of like turning on and spinning up all of these machines. There is a cost to coordinating all of them, getting them on the same page to solve a problem in this case, to generate a proof. And that cost itself will grow as you increase the number of machines. On this graph, we only plotted from 2 to the 15 onwards, but in practice, because I tried it from like 2 to the 5 and through 2 to the 10, you actually see that it starts to really cross over thresholds, so that to the point that like this will be actually the highest and this will be the lowest. And that's a natural trade-off that you're making, because as you increase the number of machines, the communication costs on network and also memory resources has to be shared, and all of those things grow. And so the real value in this is actually kind of when you start to cross over that threshold and you're looking at large problems, that it becomes useful to do a distributed technique.
Thank you.
Sorry. Although this reduces the cost of calculating a proof from a circuit, is it still prohibitively expensive to calculate the circuit from a virtual machine bytecode or whatever representation that you'd have that would be executable normally?
So are you saying like if I were to have some problem that I map into a circuit and then I want to compute this, like that process before I get to computing would still be hard? Is that the question? Or
I mean like calculating the circuit diagram from some form that a human would write.
Oh, well, so the actual computations here are happening in the cluster, so it would be solved through the system. Maybe I'm not understanding.
I'm not sure I'm phrasing my question correctly. So like, if you, for example, you want to prove some kind of smart contract, is it still prohibitively expensive to use in a real blockchain to have like a human readable language of some kind to compute the circuit diagram from that language or from a bytecode? Is that step still very expensive? Because this system starts with the circuit diagram.
Yeah, so this system itself assumes that you come to it with like a circuit, right? And the steps leading up to that are not being addressed in the system currently. To make that practical, I would say it's really not too bad of a problem right now. Certainly you have optimizations that would be helpful to basically reduce the circuit size, but from my understanding, and I don't know if Thibaut's here and wants to clarify, but there is basically some cost to constructing those circuits. It's actually a lot less than the arithmetic of the circuits themselves, and so in practice you can do that on a single machine and load it up onto this cluster just fine. It may be an hour or something, I don't know, but in practice like this still remains the bulk of the computations, which it would not be restricted to its bottlenecks on.
That's a great answer, thank you.
Any more questions? Cool.
So these graphs are useful to calculate like times, like if I have so many machines and so many circuit size, it will take me so much. Can you refer quote a reference where I can actually compare some actual use cases and try to figure out how many, like what's the circuit size. For example, like, calculate the Ethereum transactions at like so many million gas. Like how much circuit size would I need to construct such a ZK proof?
Yeah, so we didn't evaluate it for like the smart contract case, but we did 2 applications that you can find in the paper. One was actually implementing another previous paper called photo proof, and what that's doing is think of like Photoshop operations, like image transformations, and each of these image transformations is a state transition. And so if you could have like a proof that the state transition is valid and it only does blah things, and it comes from a logical, like a properly signed like a camera, for example, then you can maintain the certificates that ensure the integrity of the image. So that was one that we did, and we actually were able to get it up to like I think it was like 5 or 7 megapixel photos that on just like 32 or 64 machines, and it would take like a minute or 2. It was like pretty quick if I remember correctly. So you could use that as like a heuristic benchmark for like if I had a smart contract and I'm trying to apply some matrix operation, it's a very similar type of context that you could potentially try to map the napkin math cost to. The second application that we did was really like machine learning use cases. So there's a lot of demand for, or interest really, for having like verifiably like integratable machine learning computations. A lot of that is just linear algebra really underneath, and so as long as we can represent this in this matrix form, which we actually show it is, then you can compute a lot of machine learning techniques like linear regression and whatnot very naturally in this system, and we also highlight that in the paper as something that's in the realm of practical for small problems.
Any more questions? Oh, one all the way in the back. Hey.
Hey, can you use that approach to do delegation of proofs to a third party? And are there any ways to still guarantee privacy of the private inputs?
That's a really good question, and so that's one of the fundamental trade-offs that are being made here. Like this is a distributed system, not necessarily a decentralized system, and inherently, if you spin up a cluster, the trust model is that I assume that I trust all of these machines to be in my control and to behave honestly with me. So, if I go on AWS and I spin up a cluster of EC2 instances, then I'm assuming here that I own all of those EC2 instances and I'm not tampering that hardware in this case. It's another model to say like, hey, like maybe there's some other party that is doing this. They're spinning up an EC2 instance and I give them my data, in which case like you would need to have like another additional layer of protocols which weren't explored here, but I would think like you could do some type of encryption approaches or homomorphic encryption approaches that, while extremely costly, may get you something okay for reasonably sized problems. But that's an area that's certainly open for more exploration.
Thanks.
Mm-hmm.
Anyone else? I don't know if you can tell, but lunch is actually, I think it's been served. So thank you so much, Howard.
Thank you.